On the wireless communication CD-ROM, we are talking to Professor Bob Brodersen with the University of California at Berkeley, the principal investigator with the Infopad project. Bob, what is the main idea behind the Infopad wireless computing project?
Well, I guess the idea of the project is that we took a vertical slice all the way from the network applications all the way down to the delivery unit, which we call the Infopad, and we have various people working on all different aspects of the problem between those two extremes. There's the idea is that there's servers sitting back in the network that will provide video, audio, text, graphics, information like we see now from the World Wide Web. As well on the backbone network is most of the processing that will be needed to support the Infopad itself. So the basic idea is that we don't do any processing in the pad, the portable unit, unless it's absolutely necessary. So on this picture we have here, you see things like cell server and pad server, and those are basically the computation that's needed to support mobility or compression or formatting for different kinds of data that's going to be finally displayed on the pad. Also, we see that there's major efforts in this project are in the base station design, because we're trying to, the goal is to have 50 users in a very dense area like a classroom be able to receive full motion video. So that means we have to be able to somehow deliver this information through separate channels to all the different users. The goal is 2 megabits per user for a composite rate of 100 megabits per second. So we have a multi-access problem here, and we're looking at a variety of techniques. We're doing a chip design actually right now involved in CDMA, where we have a system that's very similar to the IS-95 system but scaled up substantially in bandwidth. Also, we're looking at other forms of radio links, primarily driven by low power and CMOS implementation issues. Then down in the pad itself, we're also driven by low power, of course, and one of the major ways is by moving the computation back into the network, but also the low power design techniques are used in actual chip designs inside the pad. The future goals of the pad are to have it as low as 1 watt and 1 pound. Right now we're about 4 watts and 4 pounds for the pad implementation. Also, I guess, working on is what are the different compression algorithms we'll use for transmitting text, graphics, and video across the wireless link that somehow are robust against errors and somehow are scalable with the various bandwidths we'll be able to have with the wireless link. And other, I guess, other example projects are optimization for capacity issues, so we have algorithm work involved in that, as well as algorithms for optimizing mobility. So you can see we're working on all different aspects of the problem. I think a key aspect of it was the fact that we were able to do optimizations across all different layers of this whole system design, and that's been impossible for us to have the pad be a substantially simpler and easier to use pad than you might able to do if you tried to optimize at different levels. The key idea is that the pad itself is absolutely as simple as possible, and that we don't require basically a hard disk or large mass storage, because most of the state of the system is all stored back in the network. So I guess how it's different from a laptop or a PDA is that we really rely on the fact that we do have a communications link back into the network, and thus the pad itself is as simple as possible. It's more, I guess there's a lot of discussion lately in the network computing, network computer idea, which is actually a fixed device which is hooked to the network, which has a similar concept in that the more of the processing is done back in the network. We're taking that one step further and making the device portable with its own display mechanism. So it's some sense an extension of the network computer concept that people are talking about now.
Yeah. So do you think we're going back to the old age where people used to have dumb terminals hooked to a large mainframe computer?
In some sense, that's kind of what this is in a way, except we have a whole network of mainframe computers, and you can connect to any one of those, so you're not constrained to be connected just to one of them. And I guess as opposed to being a dumb terminal, it's a terminal now that supports multimedia, text, graphics, and video, and audio, and so it's well above the old text terminal that was back in the old client-server days. But yes, I do believe that it's pretty similar to the advantages of having centralized storage for data and centralized services for system management back in the network is very appealing, and I think that is an important aspect of this architecture. One of the issues is where we're going with the pad design. Right now we've able to achieve extremely low power levels for dedicated signal processing functions. For example, the dedicated chipset that provides the text graphics, frame buffering, the video frame buffering, the video decompression, the pin audio interface, the formatting, all that consumes about 20 milliwatts, so it's extremely low power. One of the reasons we could do that is because it was all dedicated processing. Of course, that has a disadvantage if you want to make the pad more flexible and use it in many different kinds of environments. So we're now beginning to go to is to look at the issues on how you would make the pad more useful in more different kinds of environments, more flexible. So therefore you need more general purpose processing, programmable processing. So the strategy here is going to be in addition to the dedicated chips, is to see if we can really get the low power capability with some general purpose functionality, something more like a microprocessor-like architecture. And the interesting thing is you can have extremely low power levels in these kind of architectures if you look at the fact that most of the time in a I/O intensive situation like we are in the Infopad itself, that most of the time that the user is reading data or is getting ready to enter data, so the processor can be running at extremely low activity levels. Unfortunately, in conventional microprocessors, they can't really exploit that to the extent that we would hope you would be able to exploit, and so the power of a general purpose processor is many orders of magnitude higher than the power required from a dedicated solution. So we're trying to close that gap, and what I'm going to talk about, what's shown in these slides here, is the fact that what is important is that during very brief periods it's required for the processor to have very high throughput, be able to do computation, and most of the time it requires very low amount of activity or low computation rate. And so the way to so if you simply slow down the processor, it actually makes no difference. Slowing down a processor's clock actually makes no change in the amount of energy that the processor consumes. So in other words, the battery life is not improved at all by just slowing down the processor during the periods when it's in slower activity. It just takes longer to do everything. In order to be able to achieve longer battery life, keeping the function the same, what you've got to do is change the voltage. So we're looking at processor designs where the voltage scales dynamically very quickly with the amount of computation required of the processor. So it actually requires a loop composed of the DC to DC converter to change the voltage, the processor, some way of estimating how fast the processor can run, and then some software which can tell the processor what rate it needs to be computing at to meet whatever requirements are being required at that given time. So that's a major focus. We believe we can get more, on the order of magnitude better energy efficiency by having this dynamically scalable voltage strategy for the processor.